Welcome, everyone. I'm excited to kick off our presentation today. Our first slide is the title slide, focusing on productivity in forest ecosystems. Today, we'll explore what productivity really means, how it's measured in forest environments, and why it's so important for understanding ecosystem health. We'll also look at some key factors that influence productivity. So, let's get started and dive into this fascinating topic. Today, we're going to talk about site quality. Traditionally, foresters have divided forest lands into different site quality classes. These classes are essentially a way to categorize how productive a piece of land is. Now, when we talk about productivity in forestry, we're usually referring to how quickly and how much stem wood a site can produce. So, in this context, site quality gives us an idea of how well a particular land can support tree growth, especially in terms of timber production. Understanding these classes helps us make better decisions about forest management and planning. It's a key concept because it links the land's potential to the economic value we can get from it. And as we move through this presentation, keep in mind how site quality influences the overall health and productivity of our forests. Now, let's look at some indirect methods for studying forests. These methods can be based either on vegetation themselves or on the physical environment surrounding the forest. Starting with vegetation, one key factor we consider is the height of the dominant trees, which is often referred to as the site index. This gives us a good indication of the forest's productivity and site quality. Another important aspect is ground vegetation. Here, we look at indicator species and groups of species. These plants can tell us a lot about the ecological conditions of the site without having to directly measure everything. Moving on to factors of the physical environment, climate plays a crucial role. The climate influences what kinds of vegetation can thrive and how the forest develops over time. Lastly, soil characteristics are also essential. Soil type, fertility, and moisture levels all impact forest growth and composition. Together, these vegetation and environmental factors provide valuable insights into forest conditions, often allowing us to assess and manage forests more effectively without invasive methods. Let's take a closer look at the site index. Among all the different ways we assess site quality, height growth stands out as the most practical, consistent, and useful indicator. It's a reliable measure because it directly reflects how well the trees are thriving in a particular location. We can see a clear difference in the height growth of dominant trees when comparing sites of varying quality. On richer, more fertile sites, the dominant trees tend to grow significantly taller. In fact, their height can be 3 to 4 times greater than trees on poorer sites. This huge variation highlights just how important site quality is for tree growth. When we understand this, it helps us make better decisions in forest management and planning, ensuring we maximize growth potential based on site conditions. It ties directly into our overall goal of understanding and utilizing site productivity effectively. The richest site is referred to as quality I, while the poorest is classified as quality IV. Now, when we look at how tree height correlates with these quality classes, there's a clear pattern. For example, quality class I, which is the highest, features dominant trees that are 35 meters or taller. Moving down to class II, the trees are between 25 and just under 35 meters. For class III, we're talking about trees that are between 15 and just under 25 meters. And finally, in class IV, the trees are less than 15 meters tall. This correlation between tree height and site quality is quite important because it helps us gauge the productivity and potential of different sites based on their tree growth. Essentially, the taller the dominant trees, the higher the site quality, which ties back into the overall theme of assessing and optimizing forest productivity. The height of trees also provides us with valuable information about how many trees should ideally be growing in a given area. When we look at a specific site, we can determine an optimal number of trees based on their height. It has been established that for a particular site quality, the optimal number of trees per unit area is actually inversely proportional to the square of the height. In mathematical terms, this relationship can be expressed as n being proportional to 1 divided by h squared. Here, n represents the optimal number of trees per hectare, and h is the top or crop height. What this means is, as the trees grow taller, the number of trees you should plant decreases significantly, specifically, proportionally to the square of the height. This concept helps us balance tree density with growth potential, ensuring that trees have enough space to develop properly without overcrowding. It's a key principle that aligns with our overall goal of sustainable and efficient forest or crop management. Ground vegetation often serves as a very good reflection of the site conditions. It gives us valuable clues about the health and quality of the environment we are studying. Although there haven't been many studies on this in India specifically, we do know that certain key species in the ground flora of various forest types can act as reliable indicators. These species, often called indicator species, help us assess the site quality more effectively. By identifying and understanding these indicator species and groups, we can make more informed decisions about forest health, conservation priorities, and management practices. This approach ties into the broader theme of using biological indicators to gauge ecosystem conditions, which is essential for sustainable forestry and conservation efforts. Let's take a closer look at how we estimate site quality based on environmental factors. Essentially, we use either empirical formulae or regression equations. These tools help us establish a relationship between physical environmental factors and the overall site quality. What this means is, by analyzing measurable factors like soil properties, climate, or topography, we can predict how suitable a site might be for construction or other purposes. The key point here is that these methods simplify the complex interactions in the environment into manageable, mathematical models. And this approach is crucial because it allows us to make informed decisions early on, saving time and resources. Remember, whether we're using empirical formulae or regression equations, the goal is to accurately correlate environmental conditions to site quality, ensuring our project is built on a solid foundation. Productivity can be expressed in different ways, and two common units are energy and dry organic matter. When we talk about energy, we're referring to calories per square centimeter per year, which gives us an idea of the amount of energy captured or used over a given area and time. On the other hand, we can measure productivity in terms of dry organic matter, usually grams per square meter per year. This tells us how much organic material is produced and accumulated in a specific area annually. Understanding these different measures helps us compare productivity across various ecosystems and research contexts. It's important to recognize that both methods provide valuable insights, and choosing one often depends on the specific focus of the study or the available data. Overall, these measures are key to understanding how ecosystems function and how energy flows through them. To assess ecosystem productivity, we need to look beyond just the primary productivity. We have to consider secondary productivity as well, which is the biomass produced by herbivores and other consumers. Additionally, it's important to account for the energy or biomass lost through respiration, not only from green plants, but also from animals and decomposers, or saprobes. This brings us to the key equation. The total or gross primary productivity, GPP, is essentially the total energy captured through photosynthesis by plants. But not all of that energy remains in the plant biomass. Part of it is used up in respiration, which we denote as RA for green plants. So the equation shows us that GPP equals NPP, or net primary productivity, plus RA, the respiration of green plants. NPP itself is the remaining biomass after plants use some energy for their own respiration. Furthermore, when we expand the equation, it becomes GPP equals dm plus RA plus RH plus RS. Here, dm is the dry matter accumulated, basically the total biomass of plants and animals. RH stands for animal respiration, and RS accounts for respiration by decomposers, or saprobes. Understanding this comprehensive equation helps us see how energy flows through an ecosystem, from primary production to the losses due to respiration at various levels. It's essential for thoroughly evaluating ecosystem productivity and understanding the overall energy budget. Let's take a look at the productivity estimates of various ecosystems. As you can see, tropical rainforests have the highest mean net primary productivity per unit area, at around 2,200 grams per square meter per year. This high productivity reflects their lush, diverse vegetation and abundant sunlight. Moving to tropical seasonal forests, their productivity drops somewhat to about 1,600 grams, but they still support a substantial biomass, averaging 35 kilograms per square meter. Temperate evergreen and deciduous forests show similar productivity levels, both around 1,300 grams per year. The evergreen forests tend to maintain their foliage year-round, while deciduous forests shed their leaves seasonally, yet both sustain significant biomass, between 30 and 35 kilograms per square meter. In stark contrast, deserts and semi-desert scrublands have much lower productivity, only about 90 grams per year, and their biomass is minimal, roughly 0.7 kilograms per square meter. Extreme deserts are even less productive, with just about 3 grams per year and a biomass of only 0.02 kilograms. This comparison highlights how climate and environmental conditions drastically influence the productivity and biomass of different ecosystems. It also emphasizes the importance of these ecosystems in global carbon cycling and climate regulation, tying back into our overall theme of ecological balance and sustainability. Let's take a closer look at forest productivity. When we talk about this, we're essentially referring to how much biomass or wood a forest can produce over a certain period. It's a key measure because it helps us understand the health and sustainability of a forest ecosystem. Forest productivity is influenced by various factors, including climate conditions like rainfall and temperature, soil quality, and even the type of tree species present. For example, some species are naturally more productive than others, depending on their growth rates and adaptability. Understanding productivity is crucial for managing forests sustainably, especially when it comes to timber harvesting, conservation, and carbon sequestration efforts. A highly productive forest can provide more resources, but also requires careful management to avoid overexploitation. Overall, by studying forest productivity, we gain insights into how forests grow and how we can balance utilization with preservation, ensuring these ecosystems remain healthy and resilient for future generations. In Indian forestry, so far, the focus has primarily been on the production value of stem and branch wood. Essentially, we've looked at the main trunk and the branches when assessing the worth of our forest resources. Now, even in other countries, until recently, the practice has been similar, mainly concentrating on the production value of bole wood, which is the main trunk of the tree. This approach has its limitations because it overlooks other valuable components of the forest, but it's what has been traditionally emphasized. As we move forward, understanding these limitations helps us see the need for a broader perspective in forest valuation and management, aligning with our overall goal of sustainable and comprehensive forest utilization. Understanding the effect of any human activity or natural disturbance in a forest really depends on knowing what the gross primary productivity, or GPP, and net primary productivity, NPP, are in an undisturbed forest. It's important to realize that measuring photosynthesis directly is quite challenging. So, in practice, we usually estimate GPP by adding together the NPP and the plant respiration, which is often called RAW. When it comes to estimating NPP, we look at how much biomass increases over a year, and then we add in the estimated amounts of consumption by animals and the production of detritus, that is, dead plant material resulting from mortality. This approach helps us get a clearer picture of the forest's productivity, which is crucial when assessing how disturbances might be impacting the ecosystem. Net primary productivity, or NPP, is given by this simple equation. NPP equals B plus D plus C. Now, let's break down what each of these components means. B is the increase in biomass, So it's basically how much new plant material is being produced over a certain period. D stands for detritus, which is the organic matter like fallen leaves and dead organisms that are produced during the year. And C is the consumption of biomass by animals, so it's how much plant material is being eaten by herbivores. Connecting this to our overall theme, NPP essentially measures how much energy or organic material is available for the ecosystem after accounting for growth, waste, and consumption. It's a crucial indicator of the productivity and health of an ecosystem because it shows how much energy is remaining to support higher trophic levels. Understanding these components helps us see the flow of energy through ecosystems and how different factors influence overall productivity. Let's take a closer look at the indices used to express ecosystem metabolism. First, we have production efficiency, which is calculated as GPP divided by RA. GPP, or gross primary productivity, is essentially the total amount of carbon fixed by plants through photosynthesis. RA, on the other hand, is the autotrophic respiration, which is the energy used by plants for maintenance and growth. For various forests around the world, estimates show that RA typically ranges from about 10 to 15 tons per hectare per year, while GPP can vary significantly from 20 up to 160 tons per hectare per year. This variation reflects different forest types, climates, and productivity levels. Next, we have NEP, or net ecosystem productivity, which is defined as NPP minus RH. NPP, or net primary productivity, is the energy remaining after plant respiration that can be used for growth or stored in the ecosystem. RH represents heterotrophic respiration, which is the respiration by microbes and animals that decompose organic matter. Finally, there's ecosystem efficiency, which is calculated as GPP divided by the sum of NPP and RA. This index provides insight into how efficiently an ecosystem converts gross productivity into net gains after accounting for respiration losses. Understanding these indices helps us grasp the complex processes underlying ecosystem metabolism and how energy flows through different forest systems. These concepts are fundamental to our broader discussion on ecosystem functioning and sustainability. Let's take a closer look at how NPP, or net primary production, is related to LAI, the leaf area index. As you can see, LAI essentially measures the projected canopy area, which is the area of the ground covered by the leaves. What's interesting is that NPP tends to increase as LAI increases, meaning that a denser canopy generally supports more overall production. However, at the same time, the growth efficiency, that is, how effectively the plant converts resources into growth, actually decreases with higher LAI. So, while more leaves mean more photosynthesis potential, the efficiency of that process can diminish as the canopy becomes denser. This brings us to silvicultural thinning, which is a management practice that alters how carbon is allocated within a tree. By selectively removing some trees or branches, we can change the pattern of how carbon is distributed among the different structural components of the tree, like stems, leaves, and roots. All of these points tie back to our broader theme of understanding forest productivity and how we can manage forests sustainably. By manipulating LAI through practices like thinning, we can influence the overall productivity and health of the forest ecosystem. Let's take a look at the productivity estimates of Indian forests. Not much research has been done so far to determine the net primary productivity, or NPP, of these forests specifically. To give you an idea, one study by Misra in 1970 looked at 3 different ecosystems and their productivity levels. For forests, the net primary productivity was around 1,296 units, which indicates the amount of biomass produced by photosynthesis after accounting for plant respiration. Grasslands showed a productivity of about 744 units, while croplands were slightly higher at 780 units. These figures are important because they help us understand how much organic material is generated in different ecosystems, which is crucial for managing resources and conservation efforts. It's also interesting to see the variation across ecosystems, highlighting the differences in their capacity to produce biomass. Overall, this data underscores the need for more detailed studies on Indian forests to better grasp their productivity and role within the broader ecological and economic landscape. When we look at Indian forests, the available data gives us some interesting insights into the production and decomposition of dead organic matter. In evergreen forests, for example, the annual production of dead organic matter is about 20 tons per hectare. But what's really fascinating is that this organic matter doesn't accumulate much because it's decomposed nearly as quickly as it's produced. This rapid decomposition process helps maintain a balance in these ecosystems, preventing excessive buildup of litter. Moving on to deciduous forests, the dead organic matter produced is, on average, around 5.5 tons per hectare per year. So, it's significantly less than in evergreen forests, which makes sense given the different vegetation and climate conditions. As for dry thorn forests, we don't have precise estimates for litter production, but we do know that it's extremely low. This low litter production is likely due to the sparse vegetation and harsher environmental conditions. Understanding these differences in litter production across forest types is crucial because it influences nutrient cycling and forest management strategies. All these points tie back to the overall theme of how forest ecosystems function and sustain themselves through processes like organic matter production and decomposition. Let's take a closer look at Patterson's Productivity Index. Over the years, many researchers have tried to estimate how much woody biomass, specifically above ground, is produced in forests worldwide. These efforts have often relied on empirical formulas, which are essentially mathematical relationships based on climatic parameters like rainfall, temperature, and sunlight. One of the most influential formulas in this area was developed by Patterson in 1956. This formula gained widespread acceptance because it provided a practical way to predict biomass productivity by considering the climate factors that most directly influence forest growth. Understanding Patterson's index helps us see how environmental conditions shape forest productivity. It's a key part of our overall theme, how we can quantify and model forest growth to better manage and utilize our forest resources efficiently. Let's take a closer look at the CVP index, which stands for Climate, Vegetation, Productivity. This index, labeled as CVPI, helps us understand the interplay of key environmental factors. The formula shown here, with the variables TV, P, E, and G, is a way to quantify this relationship. First, TV represents the mean temperature of the hottest month in degrees Celsius. It's crucial because high temperatures can influence plant growth and evapotranspiration rates. Next, we have Ta, which is the difference between the mean temperature of the hottest and coldest months. This temperature range gives us an idea of seasonal variability and how it might impact vegetation and productivity. Then, P stands for annual precipitation in millimeters. Precipitation is a fundamental component because it directly affects water availability for plants. E is the evapotranspiration intensity, which reflects the balance between water loss through evaporation and transpiration versus water input. It's a key indicator of the water stress plants might experience. Finally, G is the length of the growing season in months, indicating how many months conditions are suitable for plant growth. When we put all these factors together, the CVP index helps us assess how climate conditions influence vegetation and productivity in a given region. Understanding this relationship is essential for ecological planning, agriculture, and managing natural resources effectively. So, by analyzing these variables collectively, we can get a comprehensive picture of the environmental suitability for various types of vegetation. All right, let's talk about how CVP relates to potential productivity. The key equation here is P equals 5.2 plus the logarithm of 1 minus 7.25 times the CVP index. Or this equation helps us understand how changes in the CVP index can influence potential productivity. Now, it's important to note that Patterson's formula, which this equation is based on, doesn't take soil effects into account at all. That means while it can give us a general idea, it might oversimplify the real-world factors influencing productivity. So, in the context of our broader discussion, this relationship highlights the importance of CVP as a predictor, but also reminds us to consider other factors, like soil quality, that can significantly impact results. This understanding is crucial as we aim to optimize productivity across different environments. Let's take a closer look at the Forest Survey of India's estimates of forest productivity. These figures give us a more realistic picture of the above-ground woody biomass production across different regions. As you can see, the productivity is measured in cubic meters per hectare per year, which helps us understand how much biomass these forests are generating annually. For instance, the Western Himalayas have a productivity of about 2.21 cubic meters per hectare per year, indicating a fairly healthy growth rate. The Eastern Himalayas are close behind, with a slightly lower value of 2.03. Moving to the northeast, we see a decrease to 1.66, which reflects different ecological conditions there. Interestingly, the western coast and the Andaman and Nicobar Islands show the highest productivity among these regions, with 3.85 cubic meters per hectare per year. This suggests that these areas have rich, productive forests, likely due to favorable climate and soil conditions. In contrast, the Deccan region has a productivity of just 1.35, and central India is even lower at 1.05. The Gangetic Plain is quite low at 0.8, and the dry forests of the Indus Plain are the least productive, with only 0.41. These variations highlight how geography, climate, and forest type influence forest productivity. They also remind us that when considering forest resources, we need region-specific data to make informed decisions about conservation and sustainable management. This regional productivity data ties into our overall theme of understanding forest ecosystems better, especially in terms of their capacity to sequester carbon and support biodiversity. It's a vital piece of the puzzle in managing India's forests sustainably. Let's talk about the carbon budget in forest ecosystems. Essentially, the way plants allocate carbon energy follows a specific pattern, mainly to build and maintain various tissues. Now, under normal conditions, this pattern remains quite consistent. However, when the plant experiences stress, like drought or disease, the typical allocation can shift, prioritizing different functions to cope with the stress. Most of us might think that the growth of stem wood is a major part of the plant's annual biomass increase, but actually, it accounts for less than 20% of all the dry matter produced in a year. So, a significant portion of carbon goes into other tissues, like leaves, roots, and bark. Speaking of leaves, they're really the key players when it comes to carbon uptake. The primary factor here is the leaf area index, or LAI, which measures the total leaf area relative to the ground area. The more leaf area a plant has, the more sunlight it can capture and convert into energy. But it's important to remember that carbon uptake isn't just about leaf area. Several environmental variables come into play, like light availability, CO2 concentration in the atmosphere, temperature, water availability, and nutrients in the soil. All of these factors influence how effectively a plant can absorb and utilize carbon, ultimately affecting its growth and the overall carbon balance in the forest. Connecting this to our broader theme, understanding these processes helps us grasp how forests act as carbon sinks and how they respond to environmental changes. It's a complex, dynamic system where each component plays a vital role in the forest's carbon budget. When we look at how net carbon uptake responds to photosynthetic active radiation, or PAR, we see a pretty consistent pattern across different plant species. The curve typically starts off rising as light increases, indicating more photosynthesis, and then it levels off, becoming asymptotic. This means there's a point where additional light doesn't significantly boost carbon fixation anymore. Now, when comparing leaf types, deciduous species generally have the ability to reach higher photosynthetic rates than evergreens. This is often because deciduous leaves are adapted to maximize photosynthesis during the growing season when conditions are optimal. As for temperature, the ideal range for photosynthesis tends to fall between 15 and 30 degrees Celsius, though this can vary depending on the species. Outside this range, the efficiency drops, which is important to consider when thinking about plant productivity under different environmental conditions. All these points tie back to our overall theme of understanding plant responses to environmental factors, helping us better grasp how different species adapt and perform under varying conditions. Let's explore how the intensity of biochemical reactions in photosynthesis relates to the concentration of carbon dioxide. As CO2 levels increase in the intercellular space of a leaf, the rate of these reactions tends to increase linearly. This means that more carbon dioxide generally leads to more active photosynthesis, up to a certain point. Now, an important element here is nitrogen. Nitrogen plays a crucial role because it contributes to the formation of key photosynthetic enzymes and light-absorbing pigments. Without enough nitrogen, the plant's ability to carry out photosynthesis efficiently can be significantly hampered. Additionally, it's not just about carbon dioxide and nitrogen. The availability of other nutrients like phosphate, iron, and potassium also impacts photosynthesis. When these nutrients are limited, it can slow down or reduce the overall photosynthetic activity. So, in essence, the rate of photosynthesis is influenced by multiple factors, including carbon dioxide levels and nutrient availability, which all connect back to the overall health and productivity of the plant. Plants use the energy they get from photosynthesis in two main ways. First, they use it to build new tissues, which is essential for growth and development. Second, they use it to maintain tissues that have already been formed, keeping everything functioning properly. Now, trees are particularly interesting because they have a large amount of conducting and storage tissue, especially in the form of sapwood. This means they need a lot more carbohydrates for respiration compared to smaller plants. In other plants, most of the energy is directed toward producing foliage and seeds, but for trees, a significant portion goes toward supporting their extensive vascular system and storage. This highlights how different plant types have adapted their energy use strategies, which ties into the overall theme of how plants optimize energy for survival and growth. Not much effort has been made to compare how energy is used when constructing tissues in trees versus maintaining them. What's really important about a tree's carbon budget is that, under normal circumstances, there's a clear pattern in how the carbohydrates produced by photosynthesis are allocated. These carbohydrates are used to build different parts of the tree, like leaves, branches, stems, and roots, in a fairly predictable way. However, if a critical resource becomes scarce or limited, this normal pattern of carbohydrate allocation can be disrupted. Such deviations are actually quite significant because recognizing when the pattern changes can tell us a lot about the health and status of the tree. And that's why understanding these deviations is crucial for forest management, helping us make better decisions to maintain healthy forests and ecosystems. To determine if there's a reasonable balance in how carbohydrates are distributed within a plant, we use two key indices. The first is the net assimilation rate. This basically measures how efficiently non-photosynthetic tissues, like stems and roots, are produced relative to the amount of foliage the plant has. It helps us understand how well the plant is converting its photosynthetic activity into growth beyond just the leaves. The second index is the Growth Efficiency Index, often denoted as E. This index looks at the ratio of stem wood production to leaf area. In other words, it tells us how much woody tissue the plant is generating per unit of leaf surface area. It's a useful way to gauge how effectively the plant channels its resources into structural growth, which is crucial for support and transport functions. When we talk about wood production in grams per year, this index helps us see how efficiently a plant is turning leaf area into sturdy, supportive tissue. Both indices are important because they give us a clearer picture of whether the plant's carbohydrate allocation is balanced, supporting healthy growth without overinvesting in one area at the expense of another. This balance is essential for the overall health and productivity of the plant, fitting into our broader theme of understanding plant growth dynamics. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about decomposition. This process involves tiny organisms like microfauna, bacteria, and fungi breaking down organic matter. As they do this, they release carbon dioxide, water, and nutrients back into the environment, which is crucial for nutrient cycling. It's important to note that not everything gets broken down completely. Some resistant compounds and newly formed substances, known as humus, remain in the soil. These contribute to soil fertility and structure over time. To study this process, researchers often use a method called the litter bag approach, where they place litter in mesh bags and monitor how it decomposes over time. This helps us understand how different factors influence decomposition. Key factors include temperature, moisture, and the chemical makeup of the litter itself. All of these elements play a significant role in determining the rate and extent of decomposition, which ties back to the overall health and productivity of ecosystems. Now let's take a closer look at soil organic matter. It starts with the forest floor, which includes the Oi, O, and Oa horizons. These layers are rich in organic material, mainly from fallen leaves, branches, and other plant debris that haven't fully decomposed yet. Moving deeper, we find mineral soil organic matter. This can be mixed into the mineral soil in the horizon, where some of the organic material is integrated with mineral particles. It can also form coatings on mineral particles in the B horizons, creating a complex matrix. The structure of soil organic matter here is very intricate. It's often amorphous, meaning it doesn't have a defined shape, and it tends to be black and acidic. This acidity comes from the presence of many phenolic and carboxylic functional groups, which influence how the organic matter interacts with other soil components. An important point to note is that soil organic matter can be quite recalcitrant. That means it resists decomposition, often protected by clay particles that shield it from microbial breakdown. This recalcitrance is crucial because it helps soils store carbon over long periods, contributing to soil fertility and climate regulation. Overall, understanding the complexity and resilience of soil organic matter helps us appreciate its vital role in soil health and carbon cycling, tying back to our broader discussion on sustainable land management. Now, let's take a closer look at the controls on DOM in soils. First, environmental factors play a huge role in how DOM behaves and changes over time. Temperature, for example, directly influences microbial activity and chemical reactions in the soil, which in turn affect DOM decomposition and stabilization. Soil moisture is another critical factor. More water can facilitate microbial processes, but can also lead to leaching losses. Water flux, or the movement of water through the soil profile, helps transport DOM, impacting its distribution and availability. Freeze and thaw cycles, along with snowmelt, are particularly interesting because they cause physical disruptions, releasing DOM trapped in frozen soils and stimulating microbial activity during the thaw period. Nitrogen effects, or N effects, are also significant since nitrogen availability can influence microbial growth and DOM processing. Lastly, land use and management practices can dramatically alter DOM dynamics, whether through agriculture, deforestation, or urbanization. These activities modify the soil environment and its capacity to store or release DOM. Overall, these controls highlight how interconnected and dynamic DOM in soils truly is, emphasizing the importance of understanding these factors to better manage soil health and carbon cycling in our ecosystems. Thank you so much for your time and attention today. I truly appreciate the opportunity to share these insights with you. Remember, the key takeaways from this presentation are about understanding the importance of collaboration, innovation, and continuous improvement in achieving our goals. These concepts are at the heart of the overall theme we've discussed, how we can adapt and thrive in a constantly changing environment. Again, thank you for being such an engaged audience. I look forward to seeing how we can all apply these ideas moving forward. Have a great day.